All right, welcome everyone to another OCP Tap call. This is call number 119. Today we have Jonathan Perry. Jonathan Perry is a maintainer of the OpenTelemetry eBPF network collector. His MIT PhD research focus on performance isolation in data centers and cloud networks with the aim to enhance network efficiency and reduce latency. Jonathan founded Flowmill, where he developed the eBPF-based network monitoring tool prior to the company's acquisition by Splunk. He is based in Austin, Texas, and today's talk will be about all the related work with the tail latency, right, Jonathan? If I'm not mistaken. So I think with no further ado, I will hand the floor to you.
Thank you, Ahmed, and welcome everybody. Let me share my screen. How is that? Is that visible?
Yes.
All right. Okay, so welcome to this talk about noisy neighbors, and specifically memory noisy neighbors.
Yes.
So what if I told you a story that a small group of engineers built this secret capability that allows them to run their workloads around 20 to 50% more efficiently on less hardware and improves their tail latency substantially by factors of 4, 5, or 13 times? That might seem fantastic, right? How can we not know about this type of capability? Well, it turns out this capability seems to actually exist. Although the development was not in secret, there have been papers over the last more than a decade from well-known hyperscalers and top universities that explores this capability. And today I want to give an overview about what's known about this. And the reason I'm giving this talk is that I believe that this knowledge that's out there is ready to be made into practical systems that can benefit the entire, computation community or, industry at large. So you might know some of these surveys. This one was published by Datadog, showing that many workloads, this was specifically for containers, many workloads use a lot less CPU than what we request or allocate to them. In this case, more than 65% of containers use less of half of what was allocated to them. And so I don't know if we're able to have a survey here. I'll tell you the results when I ran this survey. So I asked these 100 practitioners at KubeCon, so a Kubernetes conference, if they knew what their cluster utilization was. So I had around 40 people raise their hands, knowing their average cluster utilization of a user-facing cluster, so running interactive workloads. I asked them, leave your hand up if your cluster utilization is above 20%. And most people left their hands up. And then, is it above 30%? So around a third dropped their hand. So a third of people had between 20 and 30% CPU utilization in their cluster. Another third had between 30 and 40. And a few said that they had more than 50% CPU utilization. So clusters are very underutilized, at least from the data points I was able to collect from practitioners. And so for folks, kind of if you kind of mentally participated in this survey right now, if you know of a production cluster and you said that your utilization is between 20 to 40%, you're in pretty good company. Some of the largest companies on the planet that have pretty big engineering teams that are able to optimize the deployments have published their CPU utilizations, and the results are between 20 to 40%. But what seems to have happened in the last few years is that some companies have been able to increase their efficiency quite substantially. So if you look here, Google was around 35% in 2011 and 50% in 2019. So, well, what happened to increase the efficiency so much from these organizations? Well, having read published work, there seems to be at least two contributors I was able to find. One are advancements in vertical autoscaling. So these are systems that decide for each workload how much CPU and how much memory to allocate to it dynamically. So it learns the system and packs workloads well onto machines. And there's a very interesting paper from Google called Autopilot, published in Eurosys 2020. There are systems available generally that for in industry that enable that make these kind of decisions. So they decide for each workload how much CPU and how much memory to allocate to it. And so this is one of the contributors to added efficiency. The second contributor, which is going to be the topic of this talk, is the ability to handle noisy neighbors. And the idea here is by ensuring that applications are allocated enough resources to execute efficiently, and there's no one application that steals all the resources and starves others, you're able to get more efficiency in the cluster. So you can pack more workloads together because you know that they would interact well. And I'll cover this in the next few slides. So in this, I'll pause for question in a moment. I've divided this talk into 4 sections, and I've decided instead of giving a deep dive into one system or one paper, one implementation, and give a lot of details on this one system, I've decided to give a broad overview of what's known about it and how to solve it. This is a good time to pause for questions if there are any.
Yeah, let's go for some questions. Also, just want to add something. Like again, this is in the this presentation is brought to you by the distributed system series, which the TSIAW led by Hisham and Dan are leading.
I guess I have one
Mm-hmm.
question, John. And in the graph that you were just showing to set up everything, when I'm looking at it, is it normalized for outages and unavailable time?
So you're asking about the graph here on the top, right?
Right. Yeah.
Yes. So I cheated a little bit here, and I should tell, if I teach, if I talk to students, I'll tell them never to do this. And when I read papers, I never want anybody to do what I did here. But I took results for multiple papers and put them on the same graph, and that's why time doesn't have really an x-axis, because one of them was a week and one of them was a month, I think. And so yes, this is not normalized for outages. This is just average utilization across the measured period.
Makes sense. Okay. Thank you.
Okay. Any more questions? Okay. Okay, so let's talk about the problem. What is the memory noisy neighbor? How does it affect workloads? And is it really prevalent in existing clusters or not? So applications, everybody thinks about running in the cloud, and they have an orchestrator like Kubernetes, but these applications ultimately run on physical hardware that's in data centers, powered by real power, and you have real silicons lying somewhere. And the applications have to share the limited hardware resources that are available on these servers. What happens with noisy neighbor is that one application consumes a lot more than its fair share of resources. And so the other applications running alongside it are unable to get the resources that they need, and therefore have degraded performance. And in this talk, I'm going to focus on this memory subsystem, which are kind of the two bottom blocks here, the last level cache, which I'll just call cache throughout the talk, and memory bandwidth. So let's look at this benchmark. In this benchmark, the workload varied how many reads and writes it performed on the machine. So this changed the amount of memory bandwidth per second it varies the number of read and writes per second, and so it changed the memory bandwidth. And it measured for each imposed memory bandwidth by the benchmark, it measured the memory access latency. And as you can see in this graph, as the benchmark application consumes more and more memory bandwidth, the access latency increases. And around 80% here, or 90%, 90 gigabytes per second, there is a knee point where the access latency increases very substantially with an increase in memory bandwidth. What this means is if you have one application on the system that is a noisy neighbor and drives the entire system from the 80% mark to the 100% mark, it can cause a doubling of memory access latency for all the applications running on this server. This is essentially the memory noisy neighbor problem, right? One application that drives the entire system to this regime where all of the other applications have high access latency and low performance. And so one question you can ask is, CPUs try to hide this type of memory latency in order to protect performance of applications. There are multiple mechanisms. For example, prefetchers on CPU read memory from DRAM onto the CPU so that it's available when the program needs it without going out to DRAM. You have the reorder buffer that allows the CPU to execute instructions out of order while it's waiting for memory, as long as those instructions compute the same thing. And caches help keep data close to the CPU in case they're accessed more so that the CPU doesn't have to reread them. And so the question is, do these mechanisms actually protect programs from this high memory latency that is imposed by contention on memory bandwidth? Does our performance degrade or not? And so there's a very popular metric to measure whether CPUs degrade due to memory latency, which is cycles per instruction, or CPI. The idea here is, as CPUs have to wait for memory, they cannot do useful work. So they enter these stall cycles waiting for memory. And so the cycle counter increases while the number of instructions that the CPU actually executes doesn't increase. So the ratio between the number of cycles and the number of instructions is higher when there's this type of slowdown due to memory contention. And so let's see measurements that show us whether memory contention actually causes high CPI or slowdowns. Here are measurements taken by Alibaba Cloud. This is a trace that Alibaba published in 2022, where they measured a cluster with over 8,000 physical hosts running over 1 million containers. And they sampled these low-level metrics like memory bandwidth, memory latency, and cycles per instructions over 24 hours. What you can see here on the left is a graph very similar to what we saw a couple of slides ago. On the x-axis is memory bandwidth, and on the y-axis is memory latency. This is similar to what we saw before with the knee curve, right? You have latency, memory access latency increases with memory latency until around 70–80%, where you have a very dramatic increase in latency. On the right-hand side is a graph plotting. You can see on the x-axis is the memory latency, and on the y-axis, cycles per instruction. And you can see that as the memory latency increases, the cycles per instruction also increases. If you look at what noisy neighbor means in this environment is, if you have a noisy neighbor that drives bandwidth in this last high 20%, from 80% to 100%, it increases latency around two times, around doubling it. And this causes the cycles per instructions on the right-hand side to increase more than 25%. So this means just because you have this one noisy neighbor, all of the other applications are going to consume a lot more cycles in order to get the same work done, around 25% more cycles. So, everything becomes 25% slower just because of this. And I should say that this system measured by Alibaba Cloud here already has cache noisy neighbor mitigation. So these measurements only show how much memory bandwidth noisy neighbor affects performance. And so if you had measured a system that did not have neither of these mitigation mechanisms, neither cache nor memory bandwidth, the percent of degradation would have been a lot higher, so a lot more than 25%. This 25% is somewhat of a lower bound of how much performance degrades due to memory noisy neighbor. All right, so these measurements show that the performance of applications degrade when there's contention for the memory bandwidth. Does tail latency also degrade? It turns out that the effects on tail latency are very, very substantial. These are measurements published by Google in 2015 in a paper called Heracles. These three tables that you see here correspond to three production workloads at Google. Web search is the search node for Google Web Search. ML cluster is a machine learning text classification system that works in real time and services user requests. And memkeyval is an in-memory key value store like memcache. The rows in these tables are the different noise generators that they use. Baseline is without a noise generator. Then there are three cache noisy neighbor generators, small, medium, and big, and memory bandwidth noisy neighbor called DRAM. The columns are load on the production system, and the number in the table are the latency as a fraction of the target SLOs. So they didn't publish that they were aiming for 100 milliseconds or 200 milliseconds and so on, but they published what is the fraction that they were able to achieve as percent of their targets. So this 116% means that running with this with LLC medium noisy neighbor at 50% load exceeded the target P99, I think, latency for this by 16%. And what you can see from these tables is for all of these three workloads, there is a very substantial increase in latency when there's noisy neighbor. So for example, for web search, more than 4 times. It changes with the load on the system, but that's around 4 times and more. For ML cluster, 5 times and more. And memkeyval suffers 13 times degradation in tail latency. So this is a huge increase in tail latency because of noisy neighbor. We talked about maybe 25% average, but then the tail latency is impacted a lot more. Usually I run a survey about node sizing in production clusters, and I'll tell you just the results. I asked the same group if they know what type of virtual machines or servers that they use in their production clusters. So we had around 40 people raise their hands, and then I asked, tell me, do you only use full machines? So the entire server that you allocate your workloads on. This was a cloud conference, so a lot of them run virtual machines, and they ask for the smaller virtual machines. And in practice, I think out of around 40 who raised their hands, only 2 kept their hands up saying, yes, they run only on full servers. So it's very common practice to run on virtual machines that are 4 cores or 8 cores or 16 cores. And so, very common practice today for practitioners is to separate the big data or analytics workloads from the user-facing real-time workloads. And the reason is you don't want your big data analytics to interfere with your production workloads. You don't want to have somebody just running a big data analytics job to destroy the performance of your latency sensitive systems. But it turns out for folks running this way, they're running on the public cloud. They're not taking full CPUs. They're actually sharing their machines with some other random folks on the internet, right? Like imagine that you've gone through all this work to separate your system so that your batch workloads don't interfere with your production user-facing workloads, and then in practice you're running next to some other person's batch job, some random organization that's using the public cloud. And so this is kind of mind-boggling, you can call it. I tried to ask around if there are cloud providers and virtual machine providers that actually protect VMs from noisy neighbors, and I couldn't get a definite answer that anybody really does it. There's just there's no positive information that providers isolate performance this way. So think about it, what organizations can spend, years of engineering optimizing user experience. For example, adding database indices, changing data schemas to make queries faster, taking a big service and splitting it into multiple microservices so that processing can happen in parallel, or just regular profiling code and alleviating bottlenecks. And it's absurd that, we've put all this work in and all of it can be completely erased and obliterated by a memory noisy neighbor that reduces performance of the compute infrastructure. And so, do you really need to have these batch analytics jobs running next to your workloads in order to experience noisy neighbor? What if I actually take these full machines and I only run production user-facing services on them and never run batch analytics on them? Well, it turns out even regular workloads are noisy neighbors. In this experiment run by MIT researchers in 2020, they ran Memcache alongside a garbage collected workload. And you can see on the top graph here, the memory bandwidth. As the experiment starts, it's pretty low. But as the mark phase of the garbage collection starts, memory bandwidth is saturated, just spikes. So garbage collection can be very memory intensive. Now look at latency. It's usually around 50 microseconds, P99.9th percentile latency. But as the mark phase starts, the latency spikes more than 3 orders of magnitude. So this shows that even a garbage collected workload can be a noisy neighbor to your system. There are other examples of memory intensive workloads. So for example, if you have a live image security scanner running in the cluster, video streaming, video transcoding, or any transcoding, and even container images for people running containerized systems, they come compressed. So just decompressing a container image to upgrade one piece of software running on a server is memory intensive. Just to summarize so far, memory noisy neighbor shows up as kind of this high memory access latency, which translates to high cycles per instructions. And this just looks like high CPU. It looks like your system is working really hard, but actually it's not doing useful work. Tail latency suffers significantly from memory noisy neighbor, and we've seen 4 to 13 times increase in tail latency. And you might get noisy neighbor from other tenants' VMs running alongside you in the cloud, or your own workload can be noisy neighbor. And so this is a good time to pause for questions if there are any.
So I think David had one on the chat. What are bare metal instances? Or what about bare metal instances?
Right. So if I hope I understand the question correctly. So when you're running on the public cloud, you can either run a VM under a hypervisor, or the cloud provider can give you access to almost raw hardware, which they call bare metal. So some organizations run only on these bare metal instances, but most companies that I've talked to that use Kubernetes in the cloud, at least at that conference, used VMs under a hypervisor. And those VMs kind of share the underlying infrastructure with bare metal, with other VMs. If you're running on bare metal infrastructure, then you wouldn't have noisy neighbors from other VMs or other organizations running next to you, but you'd still have noise that your own workloads generate for themselves. So you have this problem even if you're not sharing the hardware with others. Does that answer the question?
I don't know, David, you're on mute. Could you elaborate? I see you put some other stuff in the chat. Oh, oh, David says thank you. I think
Appreciate it.
Okay, thanks. It's hard for me to look at the chat, so I'd really appreciate. Thanks, Dan, for helping out with that.
Can you hear me?
Yes.
I just had a few other questions on the specs for some of these systems. Do they have huge pages enabled? Are these also NUMA systems? Are they using anything like C groups to isolate? And then also just some of the things like BIOS settings and also thermal issues of looking at sometimes this throttling is actually if you're spiking your CPU, it may actually then have to downclock it, or it could have to do with even another server in the same cage below you, or it's in the same slot below you.
Okay, these are great questions. So let me try to see if I can answer some of them. So C groups, I'll talk about them in 3-4 slides. So we'll be covered there. NUMA, kind of NUMA configuration and huge pages. That depends on the individual paper that you can read. So some of these papers say, okay, let's turn off, uh, turn off huge pages or turn off turbo boost because they want to have more predictable performance. And so it really depends on how the system measures. This is part of the reason why research doesn't translate directly into kind of practical systems. There's a little more research to do before this becomes a real product that everybody can use, just because there are a lot of these assumptions that these papers, there are a lot of papers, so each paper makes different assumptions. That's an issue, but it just depends. Alibaba Cloud, for example, I don't know what they did with huge pages. They said what mitigations they actually run, but these were production systems that they actually ran. So
yes. And then the other question, just more at a higher level. So we're talking about things like what is the utilization of the hardware, or what is the memory bandwidth or CPI? What about total cost of ownership, and especially the electricity consumption? Because there can be cases where your bandwidth may go down, your CPI may spike, but your total cost of ownership still could be lower if you're utilizing less power than if you're suddenly trying to use things at full and then they're running at much higher clock speeds, and then your power consumption goes through the roof.
The I don't have a definite evidence in this talk. I haven't. Thanks for this question. My understanding of common knowledge in this field is that systems are very nonlinear in CPU utilization, just because, well, actually they might be linear, but there's a big offset where kind of you have to pay just to bring the machine up. Just by spinning up the whatever disks, if you have disks on there, just by spinning up the machine, you're paying 70% of the cost. And then marginally, if you use it at 20% or at 60%, the difference in power is not going to be that large. And so total cost of ownership, many companies, so this is maybe I didn't make this point, and I think it's an important point, so I'll try to make it, I'll make it now. So a lot of companies decide what their CPU utilization is going to be based on the tail latency. Companies have targets for SLOs, right? Like you're on your application, you're trying to buy something on Amazon. So Amazon is going to make sure that you don't have a 2-second click. Because once you have a 2-second click, many people just, hey, let me read my email. You never finish the transaction. And it's also kind of a bad experience, right? Like you want to be relatively snappy all of the time. And so companies, when they decide how many nodes to run, kind of, are we running on 100 servers or 200 servers or 400 servers? They decide based on this tail latency. So they basically say, okay, let's try to run at 50%. No, we exceed our target P95, P99 percentile. Let's run on 40 and 30 and 20. And that's how a lot of companies reach that 20%. If you had much more predictable latencies, tail latencies, then companies would be a lot more comfortable running at 50 and 60 and 70%. And I think these Google numbers that increased from 35% to around 50, 55%, a lot of it, I believe, was engendered by having more predictable latencies, even at higher loads. And so you could run on fewer, so total cost of ownership, you could run on half as many servers or a third as many servers if you run at higher utilization. If you're paying a little bit more power, you're still going to be a lot better off.
I just wanted to add something to what you said, Barry. So, we do deploy like multi-host systems and stuff like that when it comes to bare metal instances for Google. And you would see the noisy neighbor problem still because there's a lot of memory even on your network pipe, that, if you don't really take precaution to kind of either make reservations or, have the right policy to handle it, it'll cause the same noisy neighbor problem. There was one more point that I want to make is like, there is only so much that an infrastructure provider like, say, Google or Alibaba or whoever can do for preventing this noisy neighbor condition. There is some amount that there's something that we do in our devices, malicious driver detect. It's very, very important because, fair play cannot be always expected from, the tenants that are being hosted, not because of malicious intent, but more because of bad design or software, right? So there is like all these cases where, you didn't really submit the receive buffers, and now you are kind of creating back pressure in the pipe because no receive buffers were there. And that'll cause the noisy neighbor problem, very, very crazy tail latencies. So in that situation, what you do is you just basically report saying that this particular tenant is misbehaving and you kind of give a timeout or something, right? So that's very, very common.
Yes, I agree. There are different types of noisy neighbor, and I think you mentioned network noisy neighbor, which is relatively hard to mitigate. And I think, David, you mentioned power noisy neighbor, so you can have another tenant that's just running a lot of compute and heating up the CPU a lot more than its fair share, and then the operating system has to cool everything down by reducing frequency. There are other types of this. You can have, if you're running hyper-threaded, then you can have hyper-thread noisy neighbor where your other thread is using hardware resources kind of more than you'd like, and so on. So there are multiple of these noisy neighbor. I believe as industry, we should be able to mitigate those. It's not a fact of life that we should just engineer our systems to be so fast that even with this high variability, we still reach our goals of performance. We should tackle those actively, the noisy neighbors. We should tackle those actively if we can.
I'll add a word of caution, right, Perry? The thing is, there are resources and they are always over provisioned because you want to make money. Right. And once you provision it, of course, you will have the situation of noisy neighbors, right? So that's the reality of things. And you're hosting on a server multiple VM with the assumption that each of those VMs are not really going to use the resources that they're paying for. And that's why you're over provisioning it, right? So yeah, that's the reality of things. That's the economics, I would say, rather than, more of a technical issue.
Yes, I think whatever your economic incentive, whether you need to pack them very tightly or whether you have money to pack, to over provision resources, not oversubscribe, but over provision. So you might have an incentive to oversubscribe. You might have an incentive to over provision. financially. But I think either way, it doesn't make sense not to mitigate noisy neighbor if you can easily do it, because
Agreed.
your
Yeah, yeah.
performance suffers either way.
Yes, yes. I mean, and there are some repercussions beyond just saying, okay, tail latency is going to suffer. The bigger repercussion is the scalability of the system, right? And that is something, I mean, Google has really good research in showing that the biggest problem you suffer from is, if you needed to divide your work among X number of units, you just cannot do it if you have this very bad tail latency, right? Yeah, so
Yes, tail at scale sort of argument.
yeah.
Great. Okay, let's move on. We still have a bit of ways to go. Here we go. So let's in this section, I want to talk about what is actually available. And David asked about containers. Would those help or not? So let's take a look. So modern CPUs have support for direct control over the amount of resources that each application can use. You can decide what fraction of caches an application can use and how much memory bandwidth it can use. This is something that is supported by Intel, AMD, and ARM, probably others, right? And so these are two common knobs that you have. The other method to control noisy neighbor is to reduce the opportunity that the noisy neighbor has to consume resources. So you can limit the number of cores it's running on, or reduce the frequency of those cores that it's running on. And the idea here is if you reduce the number of cycles maximum that the noisy neighbor can use, then it has less cycles to create noise on shared resources. So there's these two different types of knobs. I get this question actually a lot, right? Like, shouldn't containers do this for us? Shouldn't containers help us? And why doesn't C group regulate caches and memory bandwidth? Well, it turns out that there are C groups for CPU and memory, but they're focused on accounting for other things. So the CPU C group is mostly focused on accounting for cycles, making sure that it counts everything. And the memory C group similarly counts mostly, there are other things, but bytes that are consumed by the application. And for example, you want to know that TCP buffers are attributed to the application that holds the socket. But not all it is lost. So C groups is not the subsystem that has the support, but there is a subsystem in the Linux kernel that regulates memory bandwidth and caches. And the reason why it's a different subsystem called res control or resource control is for historical reasons. When Intel contributed support in 2016, kernel maintainers decided to put it in this different subsystem. AMD then contributed support for their processors in 2018, and ARM is contributing support. They have hardware support. They're contributing kernel support for ARM. I'd like to now show a quick demo that was recorded by folks at Meta, led by Tejan Heo. And kudos to these folks. This is not my video, but I'll just show their video and narrate. It's called the Facebook Resource Control Demo. So here you can see a workload is starting, and on the left you can see in green the transactions per second and blue latency. The workload converged to a good point, and then noisy neighbors start. You can see this compilation job on the left, and the latency spikes and the number of transactions per second decreases. Now, if we stop the noisy neighbor and let the workload converge again, then start noisy neighbors with resource control. And you can see that the application still behaves well. It still has the high number of transactions per second while the noisy neighbors are working. So there is support in Linux. There's also support in hypervisors. There is some support. I would prefer to say there are resources on the internet explaining that hypervisor X has support for Y. But there's just such a scarcity of documentation that I believe these features are used more in very specific and kind of more niche use cases like telco and finance. At least that's my impression from the documentation. So while there is hypervisor support, there is no ready system that industry at large can utilize. And so with that, I'd like to switch gears a little bit and talk about potential mitigation systems. We said that there's hardware support for direct allocation, and there's Linux, there's support in Linux. What systems can you build that actually control noisy neighbors? So I'll go through these three major types of systems. And if you read papers, they mostly fall into one of these three categories. The first one is based on cycles per instructions. We talked about cycles per instructions, and the idea is when there's high memory interference, there's high cycles per instructions, and we can use that in order to detect cases of interference. The major challenge that the system has is that it doesn't know what a good CPI is and what is a bad CPI measurement. Right? Is 3 cycles per instructions okay for an application? Is 5 okay? What do we do? So it needs to create these baselines, and the systems measures CPI for every task every few minutes, and then creates these profiles. The system then uses these profiles to detect outliers. So if a task has an anomalous, high CPI compared to the profile for several measurement intervals, then it's declared an outlier. Once the system detects an outlier, it tries to find what is the noisy neighbor that affects that outlier. The idea here is when the noisy neighbor has high CPU utilization, it creates more noise. So the system correlates the CPI readings from the victim with the CPU utilization of all other tasks to find the node, and then it can mitigate that. The major disadvantage of this type of system is that the measurements are very, very noisy, and they need to be averaged over multiple minutes in order to make good decisions. And this is really problematic because by the time the system finally makes a decision, there's already a lot of damage done. And this is probably like the major disadvantage of CPI-based systems. And another disadvantage is that the system needs to create these profiles, needs to aggregate them, and then distribute them into each server for control. And this makes the deployment a lot more complex. But according to Google in this 2013 paper, as of the paper writing, this system has been deployed to all of Google's shared clusters. And I've actually talked to a few engineers who've used it. The second type of system is what I call latency control. So we care about application layer latency. We care about these 95th percentiles or 99th percentiles. So let's control that directly. So this system measures latencies, then computes for each task what is their percent of their target. So one task might be at 50% of its target SLO, and another one might be 98% of its target SLO, so very close to breaching its SLO target. And what the system does is it chooses the fastest task compared to its SLO and the slowest task compared to its SLO, and then moves resources between the two. So you can call it a Robin Hood allocator. It takes from the fast and gives to the slow. So this is a lot simpler than the CPI-based approach because it does not require profiling. We have the SLO targets, so we know what's good and what's bad. But application layer latency is noisy, right? Like you might have your application go to other, like a database or another microservice, and there's variability in response times for each user, maybe because some users require more computations than others. And so this still needs a lot of averaging to get a good reading. So it reacts relatively slowly. And another disadvantage is that organizations have a hard time deploying software that has uniform measurements across every service. So kind of organizationally, this is relatively hard.
Yeah, and this
The
particular,
third,
sorry,
yes,
in that
please,
particular
David.
paper, is this doing latency measurements internally within the application itself, or factoring in the network layer?
Here, every application receives requests from users and reports their own P95 and P99.
But it's based only on the internal application. So if there's additional, for example, queuing and buffering in the hypervisor or in the NIC itself, is that going to show up in the tail latencies?
I'm trying to think about the specific paper parties. I don't remember. My intuition is that they measured it at the application layer without the queuing of incoming packets.
Okay, gotcha.
Okay, so the third type of category is what I call usage control. And here the system explicitly measures the cache usage and memory bandwidth for each application. And if an application is using too much, then it limits those applications. So for example, with cache occupancy, you take the actual measurements of cache utilization per application, and then you compute a fair allocation. And maybe the fair allocation is proportional to the amount of resources that you allocated to each application. So you wanted one application to run on 2 cores and another one on 4 cores, then you want the 2-to-4 ratio in cache usage. Then the system runs these two distributions through a similarity function. So if the actual measurements are close to the fair allocation, then you don't need to do anything. But if they're far enough away, they're not as similar, then you limit the abusers to their fair share. And the question that rises a lot here is, do you really want fairness? Maybe some applications need a lot more help versus others, right? Like structurally, they're built so that they're struggling against their SLOs. And so that is a fair point. But remember that the goal of the system is to limit these egregious behaviors by these super noisy neighbors that really hurt performance and hurt the tail latency performance for every application on the system. So just by limiting those egregiously bad noisy neighbors to their fair share, you can get significant improvement in tail latency, and which it's not the optimal, but it might get you like the bulk of the benefit. These systems are very easy to build. They do not require centralized components, and you measure and control the resources directly. And so you can react very quickly to changes. And it's relatively simple to reason about, right? Like an application uses a lot more than its fair share of caches, then you limit it. So according to this paper from 2020 in Alibaba Cloud, this system has been deployed to around an order of magnitude of 1 million cores in production for over 2 years as of paper writing in 2020, which is pretty impressive. So as far as I understand, this is internal Alibaba Cloud workloads. So to summarize so far, we have these 3 categories of mitigation systems. There are a lot of good ideas out there, and I believe there are enough good ideas that we can, in fact, cobble them together to build a good solution for the entire, distributed systems, cloud ecosystem. Specifically, I like this third type of systems because they are simple and effective. And I think as a community, we should go towards these type 3 systems. And so I think that concludes the 3rd out of 4 sections. And maybe questions so far?
Looks everything's clear.
All right. I think we only have a few more minutes. Sorry, go ahead.
Dan, you have a question?
No, I was just gonna say that there's nothing in the chat, but
All right.
Yeah.
Great. Let's proceed.
Thank you. So I think we only have a handful of minutes. So do you have something else that you need to cover after the talk? I can cut short
No, no,
here if
no,
you
no,
need
no.
to.
You don't have to cut short. Like if you want to even if it spills a little bit further, it's fine. Like we have it.
No, I think we.
Whoever has to leave, they can leave, and then the recording is there. They can watch the rest.
Okay,
Yeah.
got
All right.
it.
Proceed.
Okay, so what should we do? What are next steps? So how do we deploy this, for example, on a Kubernetes cluster? And in general, what do we need to do now? So a deployment might look like this. You might have on Kubernetes, it's called a daemon set. The idea is to deploy these two pieces of software on every server. You'd have one component that I called the memory collector that measures resource utilization, and that is memory bandwidth and caches per application. Then another component, that's the interference controller, adjusts allocations, and we've talked about Linux resource control. So this component can get the measurements from the memory controller and configure Linux on how to mitigate noisy neighbor. Now, this system should also have another component, and that's an observability component, where you take the memory metrics and export them to different backends so users can look at them and analyze them. And in fact, I think that building the system, we should start with observability. And the reason is because in practice, to get adoption, operators will want to first know how much benefit they would get if they're adding another controller that can change their systems in somewhat unpredictable ways. And second, when something goes wrong in the cluster and there's some issue, operators would want to have visibility into what's happening, that the cluster is behaving as expected. And so what should we measure? If you remember this slide from before, it shows that high memory bandwidth leads to slow application. The problem is that it goes through these three mental steps, right? It says, on the left graph, high memory bandwidth leads to high access latency. Then on the right-hand graph, high access latency leads to high CPI. And then the third mental leap you have to make is when you have high CPI, then applications are slow because they use a lot more cycles and not process more instructions for these cycles. And so can we reduce this this mental leap and just measure directly the benefit to applications? And so I think kind of this memory collector should measure on the axis the contention for memory resources and how it directly affects application performance on the y-axis. And that will make a strong case to operators that they should install these mechanisms to mitigate noisy neighbors. I'd like to conclude with two open research questions that might be interesting to folks here to solve. So the first one is about representations of distributions of two-dimensional distributions. So if you look on the left-hand side, there are a handful of data structures that represent distributions. For example, T-digest, which this diagram represents, takes a distribution and represents it with what's called centroids. So these are represented by these bars in the graph on the left-hand side. Each centroid has a mean of the samples it represents and a weight, so the number of samples it represents. And the idea with the T-digest is that for every new sample that comes in, the algorithm decides what centroid to add it to and how to split and merge centroids so that this data structure maintains the ability to query percentiles with well-behaved approximation errors. So kind of this is a summary. This allows you to summarize a big distribution with maybe you have millions of samples that come in and you want to represent them with maybe only a handful, 100 or 200 floating point numbers. And so the open question that I have, and if somebody knows or has intuition on how to solve this, is how can we have data structures that represent these two-dimensional distributions? I showed you why we would want to collect these and show them to users. Can we do this efficiently? The second open research question is, about virtualization. So memory bandwidth controls in hardware, for example, on the Intel, they call it RDT, you can control memory bandwidth allocations in 10% increments. So you can allocate 10% or 20% or 30% or so. And the problem is that these allocations are per core. So if an application has 10 cores at 10%, it might utilize the entire memory bandwidth. And if you run an individual system and you have a controller that changes, that tweaks these allocations, then you can still have a well-behaving system. But how do you carry this interface into hypervisors? So what is the interface and what is the implementation for a hypervisor to have applications, so to have tenants running in VMs, be able to ask for memory bandwidth allocations, but still have a fair allocation between virtual machines? Okay, final slide. So I started a GitHub repo for the memory collector, and I would like to invite everybody who is interested to participate, or if you know folks who might be interested in this, please refer them to the project. This is called perfpod memory collector. If you want to make repository contributions, we're looking for contributors to the collector. We'd also like to develop a set of test beds and benchmarks, if that's what you're interested in, so that we can test the correctness of the collector and show memory noisy neighbor behavior as a demo. Even if you don't have time to contribute to the repo, if you just want to hear more, or if you think you can deploy early versions in some testing or staging environments, please reach out. Because we'd like to make sure that this collector supports a broad range of environments. And to finish, I want to go back to the hyperscaler CPU utilization graph, and I hope we can drive kind of industry usage to better efficiency and lower tail latency, so that more of the performance work that our performance engineers do can shine through. And so happy to take more questions if there are any.
You know, there's another effort here at OCP. It's called AI hardware software co-design, and it's not an OCP project in that they're building something imminently, but it's more of a future technologies where they're kind of researching it. And one area I think there's a lot of overlap here with is their polymorphic architectures, because you kind of have to solve the same problems to have resource controls in a polymorphic architecture. So maybe this is worth like kind of just a meeting of the minds and just kind of some cross-pollination, see if there's anything that could be shared or any insights that could be exchanged.
Yes, definitely. Thank you. I'd appreciate. Yeah, we'll talk afterwards and see who I should reach out to. Here, let me stop sharing so we can talk. But yes, Ron, do you have a question?
Yeah, maybe it's a very basic one, but if I understand, the approach is find the noisy neighbor and then penalize it. But what if the noisy neighbor is part of your task, right? It's just that he's taking more resources than the others. It's just not doing a fair share, and therefore the entire tail latency of all your processes suffers. Is that also a target? That is, you find someone and you see that it's not optimized, and then you fair share it and get a eventual latency which is better.
So I think I'm trying to let me paraphrase your question to see if I understand it. So I think your question is, could it be the case that some component of the system that is critical to its performance is built in a non-optimized way, so that it is always detected as a noisy neighbor? And so if you try to mitigate noisy neighbor, you're actually hurting performance of the system rather than aiding it?
for example, but I was trying to look at it on a more positive approach, right? So I am running a very big, I don't have neighbors which are not part of my tasks. Like, so I have a very big task, and I'm interested in the flow completion time of the entire task, right? And what I see is that I see that I'm over the knee, and therefore my entire task is very slow, right? So I'm trying to figure out how can I improve that, right? But I cannot kill part of my flows, right? I just need to find an optimization such that some of them don't use the memory as eagerly, but maybe are doing computation or something of that sort. And therefore, you don't penalize and remove something, which is, you just need to find the right optimization.
Yeah. So with these systems, the way I think about them is if you have one noisy neighbor component in the system that is driving the system from, let's call it 80% to 100%, you want to keep the entire system at 80% so that it has good latency behaviors. And the way you could do that is scaling every process down by 20%. Right? If you do that, then the entire system runs in a more optimal point performance-wise. But then maybe your throughput suffers because the task that was driving the memory to memory bandwidth to extremes is now slower. But then if you really want to have this type of performance profile, you should, and you have a load balancer, maybe you can run on more machines and spread the load, right? So instead of running on 5 machines, run on 6 machines, you'll have a much better performance profile. You'll have to pay more for it, maybe. I think you'd have to actually pay less, and either way, just by making sure that you're more efficient. Actually, no, if your bottleneck is memory bandwidth, then that is your bottleneck. Right? So then you'll have to pay more in order to get better performance. But many systems are not bottlenecked by memory bandwidth. They're only occasionally bottlenecked by memory bandwidth for non-critical processes like garbage collection. So garbage collection can take another 10 milliseconds or 100 milliseconds to make everybody else have a much more predictable latency. And you'll just pay it over longer time, that intermittent requirement. If your system is always saturated on memory bandwidth and you need to lower your response times, lower your tail latency, then you'd have to spend more hardware to run it. Does that make sense?
Yes, but you're not going to penalize your memory garbage collection, right?
I think you should.
Okay,
if I care about latency, about predictable latency, and once every 5 seconds, I have 100 milliseconds of high memory bandwidth because of garbage collection. Yes, I want that garbage collection to take 200 milliseconds, and then all of the processes on the system would have a lot more predictable tail latency, which is better.
Yeah, depending on the system, though, because sometimes that one doing the garbage collection may be in the critical path and a DAG of different sort of isolated systems. So I'm thinking examples like finance, where it's a matching engine.
Okay, thank you.
Yes, you're right.
I'm also curious too, has there been research yet at looking at, so we have a noisy neighbor, but sometimes it really is, there's a certain magic threshold where you fit in cache. And then if you exceed that, everything goes to hell. Are there cases of looking at, well, how many other non-noisy neighbors can I put on a machine with a noisy neighbor? Really, how do you right size it and find where that exact threshold is to optimize performance and avoid that?
Yes, that is a great question. So there's another whole type of system that I did not mention, which is a scheduler-based system. So I talked about localized arbitration of resources, but what you could do if you had a cluster orchestrator, the cluster orchestrator could decide never to put more than 4 jobs on this node, or maybe never co-locate these two workloads together on the same node because they know they conflict. So definitely that is another knob that you can use. Another influence mechanism.
And I mean, we talked a lot about memory and CPI. I'd be curious because I think it's only just starting to come up now, where you have these massive core packages with multiple CCDs inside them. Of how do you actually manage things like the inter-core communication, where it may not be hitting to the uncore to go to the memory controller, but really the communication of the fabric itself. And to be honest, I don't know how much Intel or AMD currently even discloses about this, of what the capabilities are, to what extent they can bottleneck when you start having, 64, 128, 256 cores in a single package trying to communicate just within the package itself, what that does for latency and performance.
Yeah, good question. I don't have an answer there.
It's so early on. I'm not surprised it's not in the research yet, because they really just saw this explosion in the last few years. So.
Yeah, my hypothesis is part of the fact that you're seeing this knee curve around 70-80% is this is very familiar to network engineers, right? Like, we know this, and I think it is because of part of it is because memory requests have to traverse this interconnect.
Yep.
Yeah, so I don't know how to explicitly measure interconnect. I haven't seen work on that, but if there are performance counters that give you that can give the operating system visibility into how much each core is waiting on these, or how many of these, how much of these resource is used at any given, per second, then similar control mechanisms can be used. So the system, instead of measuring memory bandwidth, it would measure, or last level cache misses, which is a counter that's available in most CPUs. You can measure whatever that is for inter-core communication. But yeah, don't have a definite answer.
And one other you touched on is something I spent a painful amount of my time dealing with, is how do you do these two-dimensional histograms? One of the things we found out when you're looking at it at the network level for sort of system-wide reaction time is that if you do only a 2D distribution, you actually lose a lot of structure because of some of these dynamics like overclocking or queuing, where you'll actually have these very distinct states where you have different distributions that bounce around, but they get aggregated together and you see what you have. But if you then do a temporal component bucketed over, I don't know, per second, per minute, whatever, you can then detect some of these anomalies in the system that are actually impacting latency. But how to do that properly was an interesting question. I actually put some interns on it, I think 7 years ago or so.
I see. So what I hear is basically, maybe I don't want, maybe you don't want the system to measure just pairs of points of memory contention and application layer latency. It needs to be a vector because it also needs to have the core frequency in it, for example. Right. So there are other things,
a lot of other settings that are going on under the hood, and there's a whole host of them, but you start to be able to pick them out and be like, okay, now it's in this mode, then it's in that mode, and you see it bounce around.
Yes, thank you for that. That's thank you for not letting me build it and then fail on that. So yeah, now at least
it's
I
good
know
to have as a first go, but it's just once you build exactly that, then you start fitting these different like queuing theory models to it, and it works well. But then it ends up blurring out this structure of you actually have like 5 or 6 different very distinct states that you can pick out like fingerprints that get aggregated together depending on the bucket sizes you choose or the window you're aggregating over.
Yeah, thanks. Makes sense.
I'd love to talk more later. This is great.
I'd love to too, as well.
I think we have the WhatsApp group for distributed systems, and you are member of the group, Jonathan.
Yeah, correct.
David also is member, so we can continue the discussion in this group.
Yeah.
Mm-hmm.
Yeah, let's do
Bijan
that.
also is member, so we can continue there.
Yeah, that's great.
I'd love to. One of the ones I'm most curious about is on the power consumption side, because when you start really upping the clock frequency, it doesn't go linearly. So I would expect there are actually a lot of cases where it actually makes sense to have a much larger footprint that you want to run and just run it at a much lower clock frequency.
Mm-hmm.
But then the problem is, how do you, well, it's not that difficult, but how do you do the instrumentation? But typically the engineers are looking inside the machine and not, okay, what is your total footprint? And then not just the consumption of the machines themselves, but what are we paying at the data center level to then cool that as well? Unless you have all of that instrumented and you can have sort of a world view, it's actually difficult to get the metrics. If you're on small scale, like tasks, then you can actually do it properly. But
So you're saying if you already are running all the servers and they're idle, It's a lot better than rather than keeping, using 10% of the servers and 90% are idle and using 10% really hot. Maybe use all of them relatively cool. And
or
that's
somewhere in between, depending on the
Mhm.
threshold. But like I have some machines right behind me that when they're doing nothing, it's running at like 100, 200 watts, but it could spike to massively, factors of 20 or 50 times that. But do I really want it to, or do you just run it, low and slow?
Yeah.
Very cool. That was an excellent presentation. Thank you so much. I really enjoyed this.
Thank you.
I have a question,
Mhm.
Jonathan. We can continue discussing it later, but at some point in time, I was looking at side channel attacks, or which, and one form of it is covert channel. And for example, you can have some intruder um, use some software, maybe in a virtual machine, where it can look at memory, for example, reads and writes and access, and from that it can infer some information about other virtual machines or other users. But I am not sure there is a solution for this problem. But do you think one of these techniques you described can help detect those type of intruders who can steal information by looking at memory access, for example, and use it for malicious reasons?
Mhm. Um, I I'll tell you my intuition.
Yeah,
There have been these timing attacks where if an algorithm is not engineered to hide timing and have very consistent timing, then you can measure how timing varies across, different inputs to your cryptographic algorithm, and then you could recover some secret information. In the case of memory noisy neighbor, there's definitely information leaking through, but I think the information density there is very low, right? Like you have a few, let's call it a few bits per millisecond that you can get, but um, they're they're very diffuse. I think it'll be so famous last words. I think it'll be exceedingly hard to to actually like recover secret bits using looking at memory interference. But that's just my intuition. So it could be there are bits leaking, right? Like if you don't have mitigation, you could observe memory bandwidth utilization of another system. Now the question is, can you actually do something reasonable with it to get secrets?
yeah. I don't really know how to solve this problem. I haven't seen a concrete solution for it.
Partly, you could do custom hardware. You could do isolated caches and find other ways to mitigate it. You don't take the performance hit.
Yeah, I was working with a confidential computing group, you know, and some of them are in Berkeley, but they talk a lot, but and I attended some of their summits, but I haven't seen really a concrete solution will solve this issue. Other than like what you said, put the whole virtual machine in a container, hardware container that cannot leak anything. Something like that, yeah.
You get like different caches per thread, similar to the state space of the register, but do it at a cache level, which, I mean, with the densities we have now, that actually wouldn't be that difficult. I wouldn't be surprised if we did go that direction at some point. Or you just give everybody their own core. I mean, we're basically heading there where core counts are exploding. I wouldn't be surprised.
Yeah, and I've talked to Intel folks at KubeCon in November, and I haven't followed through kind of just to deeply understand what they were proposing, but they said that modern Intel processors, at least, have these three domains of cores where each one has its own memory bus as far as access to the memory interconnect or something. And the way these chips are usually configured is that every core can access all of the memory ports and all of the cache. But that is, you can optimize it so that each domain is local to that domain, has only local access to its ports, memory ports and caches. And this kind of isolates different fractions of the CPU. And so it doesn't give you per core control, but it gives you per third of the core's control, as far as I understood what he was saying. I hope I got it.
That's what we've been doing for years. So we like with NUMA nodes, for example, where you can then say, okay, we're only going to allocate memory on this particular NUMA node on the CPU. We're going to know which NICs are directly physically wired to it, and it's PCI Express controller on chip, and then you can get a lot more control and mix this. The only downside is that you're paying for a lot more sockets, but it does work, at least historically.
Well, you can get it sub-socket, but only a third of the socket. Apparently, that's what I understand.
Very cool. Well, I have to head out, but again, thank you so much. This was
All right,
tremendous.
thank you. Yeah, thank you so much for coming, everybody. I hope you enjoyed. And if you have feedback, please reach out to me, like either on WhatsApp or email, whatever works for you. Happy
All right.
to improve.
Yeah, thank you very much again, Jonathan, and we'll see everyone next week with a talk by Pat Helen about yours, mine, and ours.
I love it.
All right.
Thank you for the invitation, Hasham, and Ahmed. Thank you, David.
Thank you very
Thanks,
much.
everybody.
And great presentation, Jonathan. Thank you very much.
Wonderful.
Thank you.
All right. See everyone. Bye.
See you.
Bye.